Institute Research Associate at Stanford University before joining Dartmouth. He has expertise in developing computational models of different cognitive processes at multiple levels of complexity, as well as designing and conducting human experiments to test predictions of these models. More recently, he has been developing computational models for measuring adjustments in choice behavior and neural responses across species. The long-term goal of his research is to reveal computational principles and neural mechanisms that allow humans and other animals to be flexible. I'm very pleased to invite Dr. Alireza Soltani to the stage. The stage is yours, Dr. Soltani.
Thank you very much for the nice introduction and for inviting me and having me here. Can you hear me fine? Yes? I hope you hear me fine. Okay. I couldn't activate my, so I hope you can see my screen. So I couldn't activate my mouse, but I will just point where I'm talking if it's not clear. So today, again, thanks for inviting me. It's a bit early in the morning, so hopefully I will wake up slowly. But today I'm going to share some of the work we do related to flexibility in behavior. And what I want you to remember is the link between uncertainty in the environment and flexibility in behavior. That uncertainty in the environment actually helps all animals to be more flexible. So the reason is that the world around us changes all the time, constantly, and at different time scales. So it can be starting from the quickly changing sensory information that fall on our retina. In this case, the change in reward feedback we get from the environment. The changes happen to day-night cycles, and also seasonal changes. So basically, we live in a world that is constantly changing, and to be successful and to survive, it's important that we detect these regularities in the environment, the regularities in the changes, and so it's very important. And because if our brain is able to detect this regularity, there are at least two benefits in that. One is that if you detect them, you can make prediction to adopt proper response and behavior. For example, you can predict to forage at the right time of the day, and make choices at certain times that are more successful. The other important thing is that you can use deviations from those predictions to adjust behavior when the environment changes. So, for example, when you go to a new habitat, where the animal goes to a new habitat, they can see. Sorry, when the environment changes and the predictions are not working, you can detect that, okay, it's time to move somewhere else because the environment maybe is not good anymore. So the challenges with this, of course, it's not very easy to make prediction and also figure out deviation from those predictions. So two challenges. One is that detecting any regularity in the environment requires integration of some sort of signals over multiple time scales. And I say multiple time scales because this cannot be done on one time scale. You need more than one to be able to compare and see whether there is something happens in a specific, in a regular format. And then the other challenge is that there are also uncertainty related to regularity in the environment. So the moment that there is change, and maybe there is some logic to that change, there is some regularity, there is also uncertainty associated with that. And that makes it difficult to dissociating these different types of uncertainty makes it challenging for the task of the animal to survive. So the good news is that our brain has uh, different mechanisms for processing information at different time scales. So if you look at short-term synaptic plasticity or long-term potentiation depression, they can actually integrate information at the at the level of few hundred milliseconds to hours and days and so on. Um, there are also mechanism at the level of neural activity that reflect some sort of processes, certain time scales. And then you could also have different changes that happen at the level of circuit, and with the help of neurotransmitters that basically allow the brain to process information at different time scales. So basically, there are different cellular, molecular, and circuit level mechanisms to integrate information, to process information at different time scales. So it seems that our brain has evolved to to deal with changes that happen in the environment, and these changes can happen at very different time scales with different mechanisms. So the two questions that I'm interested in trying to understand and connect this basically these neural mechanisms in the brain and behavioral changes is that environmental changes is that the two questions that I want to look at especially here is that how does the decision maker adjust to different types of uncertainty in the environment. So this is at the behavioral level. So there is uncertainty in the environment. We want to know how the decision maker adjusts to those different types of uncertainty. And the other question is that ultimately, I would like to understand what happens in the brain. What are the mechanisms in the brain? And for that, we need to understand how neural processes um, adjust to different types of uncertainty. And so today, in this talk, I will try to provide um, some of the new work we have done trying to answer this question, some of the methods that we have developed to answer these questions, and I show you how they can be applied to different situations. So in terms of the first question, you think about an agent or decision maker moving in an environment, making choices, and this is how it would interact with the environment. The choices will change the environment, and then the reward feedback and sensory signal is the feedback the agent or decision maker uh, gets from the environment. And so to answer the question about just the different uncertainty in the environment, I will need to define what I mean by uncertainty, maybe more specifically. One, so there are different types of uncertainty. One type of uncertainty is that, as you know, everything in the world around us is probabilistic. Everything happens with certain probability. Nothing is for sure. And so this probabilistic nature of outcome, in this case, reward outcome, we are looking at reward learning, introduces some sort of uncertainty, uh, which some people call expected uncertainty. Just like basically you toss a coin, there's an expected uncertainty that it would be head or tail 50% of the time. Now, on top of that, there is the probabilities, reward probabilities can change over time. That introduces another form of uncertainty that's kind of unpredictable. So that's another form. And you could also have uncertainty in terms of the model of the environment. And what I mean by correct model of the environment is the type of association that exists between a choice and reward outcome. So what aspects of choice predict reward outcome? This is not clear. There's uncertainty about that. You may make a choice and get reward, and your choice could be made of many different things, and different features of your choice could predict reward at different time. So that also could change over time. Some action that you take that is rewarding now may not be rewarding tomorrow, which indicate that the environment has changed, either because you have influenced the environment or just the environment has changed by itself. So there are different types of uncertainty, Today, of course, I'm talking about these different types because I want to show you how we can look at this adjustment for these different forms of uncertainty. So, so the goal here for the first part of my talk is to show how we can go from detect the effect of environmental uncertainty on behavioral adjustment, how the behavior is adjusted according to different types of uncertainty in the environment. So before diving to that method that we have developed recently, I would like to just briefly mention how people measure behavioral adjustments, because that's we need to have something for that. And the basic approach is that people measure different metrics, for example, performance, um, to see whether the probability of choosing option A versus B, how it changes over time, depending on whatever parameters you're changing the environment. There are other things that behavioral neuroscientists especially use, which is called win, stay, and lose switch strategies. So it's a very old way of looking at behavior, which is we calculate the probability that the animal repeats a choice after winning, after getting a reward on that choice. So that's called win, stay. It's a conditional probability that you stay on a choice even that you won on the previous trial you chose this option. And lose switch is basically going away from the what you have chosen because you did not get a reward. And so people have been, and it can be other probabilities that people measure. The issue is that they are very limited in what they can reveal in terms of adjustments. And the reason is that they are a lot of these things are related to each other and may not be easy to dissociate from each other. The other approach that people use is I can call it like more model-based approach. In that case, you look at the behavior that you want to study, and then you fit the choice behavior with different computational model. You find the best model, and then examine the parameters in your best model. So, for example, you may use a reinforcement learning model which has a learning rate, and then try to see whether that learning rate that you estimate um, um, changes according to the uncertainty or other changes in the environment. So this looks more promising, but fitting choice data requires many trials. So you have to use many trials to estimate a set of parameters. And then the issue is that because you need many of those, many trials, you can't really look at the adjustment that happened quickly. So you can compare maybe one day of experiment with another day of experiment or different sessions of the experiment, but you can't measure the adjustment continuously because of the fitting choice data and the number of data you need for that. And at the end, whatever you do, the result that you will have is model specific, meaning that what you detect is really specific to the interpretation, is specific to the model that you have chosen. It may not be maybe very general. So what we try to do, we try to develop something very simple based on information theory to basically connect behavioral adjustment and environmental uncertainty. And to give you a notion, I will explain what is the method quickly, but why information theory could be useful here. Simple reason is that you can use information theory to measure consistency, randomness, surprise in choice, reward, feedback, etc. It's basically designed to do that, and also to connect different processes. So like choice and reward feedback. Um, well, again, these are all both probabilistic things, events, and they can be linked together using information theory. So we show you in the next part how we can do that. And the other thing is that because of the link they can provide, they are basically independent of any models. Like they are not specific. They just measure any relationship. You can use them to adjust, sorry, to detect adjustment in behavior, and then I show you how you can move with the second model-based approach to detect or understand the underlying mechanisms. So I'll go to the first part. So just give you a simple example. If you look at the basically behavior of subjects, animal, human, um, in the task, choosing between two options A and B, so two alternative free choice tasks. So you can see I just made an example. The probability of choosing A is 11 over 17. So that's one way of basically quantifying it. But you can also apply what is called Shannon entropy here, which is probably some of you are familiar with, but it's a way of measuring the, the uncertainty, randomness, surprise in a process. And you can calculate it by probability of P of X, in this case choosing A or B, times the log of P of X. And then you add this over A and B, and then you get Shannon entropy. And what tells you basically if the probabilities are close to the edges, like 0 or 1, the entropy would be small. And if they're close to 0.5, you get the maximum value. So, so entropy is maximum when the animal, in this case, choose A and B equally. But another way of looking at this, to think about some strategy that I mentioned earlier, whether whether you will select what you have been choosing because you got reward or not, is to think about the sequence of choices in terms of switch and stay. So this is a switch, this is a stay, and so on. So you can think about it not in terms of whether choosing A or B, but whether the animal is continuing in their behavior or they're switching to another option. And again, in this case, I can calculate the probability of stay is 5 over 16. And I can calculate the Shannon entropy in terms of stay and switch. Now, it provides different information. It's not about choosing A versus B, and it's more about the choice of strategy going from one selection to the other one. Now, we can do better than that, because what we care is we want to actually link choice outcomes to reward outcomes. So here again, this cartoon, A and 0 means A is not being rewarded, B and 0 means B is not rewarded, and so on. So now you can get a better idea of why this animal was choosing A and B in this specific way, and you can see that A to B here it was a switch, but it was a loose switch. It's basically the animal lost and then switched to the B. The next one here, for example, is a win state. The animal chose A and got rewarded and stayed, and so on. And that is the metric I was mentioning earlier. You can calculate the probability of win stay, which is the conditional probability that the animal stays on the same choice as the previous trial, given they got reward. And in this case, this is 4 over 7. Now, you can also calculate probability of loose switch, and it's 6 over 9. And as I mentioned, people have been calculating these values for a while. The issue is that with interpreting them is that, well, depending on the probability of win and the overall probability of stay or switch, you can get different numbers. So even though it looks like, actually in this example, they're quite similar to each other, but I could create an example where the win stay was larger than loose switch, and people usually attribute that to the animal learning more strongly from winning than losing. And that's not exactly correct. So now, if you want to extend these probabilities to a measure based on information theory or a metric, you can calculate what is called the conditional entropy. So is H of strategy given reward. So knowing the reward outcome in the previous trial, you ask whether what is the surprise in animals staying or switching. And this is again just an extension of what I show you, which is this is now joint probability of reward and strategy times the log of probability of joint probability of reward and strategy divided by P of R reward. This is very simple, but again, and people have been using this kind of quantities looking at neural data in computational neuroscience, but not in terms of behavior, and I don't know why. It's quite surprising. So anyway, this is a new metric that we propose. It's called conditional entropy. We call it conditional entropy of reward dependent strategy. A big word, so we call it ERDS. And that's one metric that you can create, but you can create all sort of other metrics to measure the relationship between what happened and the animal strategy. And I will show you how this thing will work. But just before showing you that, this piece here, which is the dividing a joint probability by a probability of reward, is actually win state, lose switch, etc. So basically, these are the conditional probability that people have been using. But now, all of them are combined into one values. So to give you a little more intuition here, more mathematical intuition, you have an input, which is a discrete random variable. You have a system here that processes information. There's an output. And so this is basically, in terms of information theory, you can think about it that you have Shannon entropy in X and Y, which is how much measuring how much randomness you have or uncertainty you have in X or Y, and higher entropy means more random. And then you have these things, which are conditional entropies, which measure basically how much entropy is left in X if you know Y, or how much entropy left in Y if you know X, etc. And the link between the two can be measured with mutual information, which is how much information is shared between X and Y. That's really the simple relationship here. That is, it's a general framework for information theory, and probably most of you know about because you're studying at Sharif University. But how it's related here, you can see it this way. Now I'm thinking about the input here. It could be the previous stimuli, choice, reward outcome, but you can think about it in the simplest case, win or lose, whether the animal got reward or didn't get reward. Now the output, which is choice strategy, is to stay or switch. So now this conditional entropy of reward dependent strategy basically measure the link between the two. But as I said, this is not limited to this link. You can do it with any quantities that you care about. You can even include other things like neural activity here. The point is that you're asking whether there is information, if you consider certain event in the past, about predicting future. I mean, here it's his relationship is in the past and future, because this reward happened in the past and the strategy is the future strategy. But it could also get the same thing. So you can actually compute different types of conditional entropy to examine different types of reward associations. So it's very general way of looking at behavior this way. So I'm not going to go into detail, but in a recent paper, we showed that basically all these metrics, what's called entropy-based metrics. Sorry, you don't see my mouse. We use that data from mice and monkey in different labs, and show that these metrics can actually predict matching behavior, and better than previous metrics that we knew about. And they also, so using that, you can actually come up with better models. So in a way, they can connect local strategies to global behavior. So basically, how a matching behavior, which is which quantifies how animal links the reward they get from different options and the time spent on those options, how it can emerge from basically responding to reward feedback in a consistent or inconsistent way. But what I'm going to show you here is more recent work, where we try to use these metrics to detect behavioral adjustments, not just to look at the global behavior, but actually look at um, um, changes in behavior over time. So here I'm looking at two tasks, and for most of this work, we look at data from different animal models. And the reason is that um, we care about detecting adjustment in behavior, and and I hope that there is something shared between different animals. I don't think they should be similar, but there should be something shared, and that kind of motivate us to study different animal models. If there is nothing shared, I think we should just stop studying different animal models, or at least using them to understand human cognition. So these two tasks are similar in terms of structure. They're kind of identical, but in the mice experiment, so the mouse is choosing between a leaking left or right, in the two tubes that are in their mouth to get reward juice. The monkeys are looking at two options, A or B, and this option can change, and they get reward. But the reward outcome is probabilistic with a very similar schedule in both animals. And as you can see here, they're able to um, to follow the better option across blocks of trials. What happened between blocks of trials that happen randomly, the good options and bad option can switch, or the probability for them can change. So they could be, equally rewarding, or one could be much better than the other one, and so on. But both of them probabilistic, the reward outcome, and also in both tests, the reward can change over time quickly. Um, so there is frequent and unpredictable changes in the environment, and which basically gives us um, the notion that is both expected and unexpected uncertainty in the environment. So we try to look at different quantities that exist in this task, and the simplest one is you can think about the probability that the better and worse option provide reward. So PB minus PW. And if this probability is larger, then there is less uncertainty in identifying the better option. And if they're close to each other, then there's more uncertainty. It's more a difficult task. And what we can do is that you can calculate probability of better. These are the distribution. Um, Different color here means less and more. Uncertain environment. So you can think about it, less is an easier when the probability is farther from each other. So as you can see that, the animal does better in the less uncertain environment. But now the metrics, what it tell us is that the entropy in a strategy, which measures how random the animals are, is actually increasing in more uncertain environment. And this is reflected in the conditional entropy, which tells you that the animals are less consistent in their behavior, in their strategy, knowing the reward outcome. So basically, they don't follow win lose switch as as consistently in the more compared to less uncertain environment. If you look at the monkeys, you can see again, of course, the performance is affected the same way by the uncertainty, but that doesn't tell you how. And here you can see that there is a decrease in the strategy of the animal. So basically, in these two species, the uncertainty about the better option make the mice basically to have more random choice of strategy and be less consistent in terms of using previous reward outcome. But in monkeys, seems to be a trend of decreasing entropy of choice of strategy. So basically, when they're dealing with more uncertain environment, actually they try to be less random to maybe reduce the uncertainty in their behavior, maybe detect the options better. We'll see later what we can tell about that. But basically, this is a simple example of how we can use these metrics to figure out what is going on or detect some adjustment to some aspects of the task. In this case, the probability of reward on the better and worse option. So as I mentioned, this task basically requires switches between blocks of trials where the better and worse option change. And what is possible, as I mentioned to you earlier, is that the animals in this task, they have to basically expect, figure out when this block switch happens, because if they do, they can quickly adjust their behavior. Now, so they can form an expectation trying to predict what is the block length in this task. And so you can basically create a simple model and for detecting that, and you call basically blocks, divide them according to whether they're shorter or longer than expected. So recently, if you have seen a bunch of blocks that are around 30 trials, now if you are basically in a trial that is 40, this is longer than expected, etc. So basically, this is going by detecting regularity in the environment. So SE means shorter than expected, LE means longer. Now you can basically divide the trials based on this notion of shorter and longer than expected. And what you can see that in mice, the probability, the performance is lower for when the blocks are shorter than expected, because when they are better when they are shorter than expected, then it's longer than expected. And the reason has become clear is that the conditional probability, the consistency in behavior actually is higher, which means that when the block gets longer than what they expect, they start acting more random and more inconsistent. Perhaps because they expect the environment to change. Now, if you look at the monkeys, you can see that there is no effect on the performance, but again, you see that the conditional entropy is higher, just similar to mice. So basically, there is expectation about block switches that happen in both animals, and both of them seems to be following using less consistent reward dependent strategy. There are other things here that I'm not going to explain. You can read the paper that just published recently. But the idea is that sorry. The idea is that you can use these metrics and detect some sort of adjustment in behavior. Now, you can, if what we say about the expectation of reversal is true, that then you can use that to see whether when the animal is in a block of trials and it passes, the trial number passes what they expect to be the length of the block, the behavior should change. And this is basically showing that. So this is probability of better before, sorry, in A, the probability of better before and after L block switches, basically. And on the right of that, you see the probability of expected L. So nothing has happened, but that's what the animal expect to happen. And as you can see, the performance goes down because, again, they try to switch their behavior. In this case, in the case of actual, when you look at before and after L, well, the environment has changed and the performance will drop because the animal has to adjust their choices, and they haven't. Now, before EL and after EL, expected block length, basically, there is nothing happened. Nothing has happened in the environment. Only the expectation of animal make them to start acting differently. And you can see that in panel B, in terms of ERTs, how consistent they are with respect to reward feedback they receive. And you can see that they similarly become more inconsistent. And you can zoom into that and calculate the mutual information, which gives you more information here. And basically, mutual information tells you the link between previous reward and strategy. And in both cases, after the actual block switches or what the animal expect to be the block switches, the link gets smaller. So the animal cares less about reward outcome. But I'm not going to detail of it. You can calculate this mutual information based on the reward feedback or option, and it seems to be the difference for mice to be in terms of option, meaning that whether they will repeat what they have chose in terms of better and worse option in the previous trial or not. In monkeys, you see similar behavior, but a difference in terms of the animals change their behavior after what they expect to be the switch. And they do that by listening to reward feedback differently. So there's a difference in how monkeys and mice respond to form this expectation and respond to this change in expected reversals. Let me just make it a little easier to be careful about time. Is that in one case, the animal is getting reward feedback, but because they expect that the environment is changing, they try to listen differently to this reward feedback. They try to listen less to the reward feedback. In the other case, the animal knows this which side is better. So better is, let's say, A is better than B, or left is better than right. And what the animal trying to do is trying to be less consistent in terms of repeating their behavior, because they expect that the better and worse option can actually change, and so on. So you can see that both of them are consistent, they're logical, adaptive, whatever you call it, but they are different kind. And you can see that the mice and monkey do actually adjust differently. So the last thing I want to say about this is that you can feed the choice data after learning all these things with using these metrics. You can feed the choice data using RL model, reinforcement learning model. In this case, we are estimating alpha, beta, and a decay parameter, which tells you what happens to the value of option you didn't choose. And you can see that there are differences in the mice behavior. You can see that there is a, with the less and more uncertain environment, forgetting gets smaller, but when you think about the expected reversals, the gamma decay gets larger, which means that they are forgetting faster what they have learned when they think the reversal actually has happened, even though nothing has happened in the environment. You can do the same thing. So the model that fit the monkey's behavior is different. You don't have the forgetting in it. You just have learning rate and the temperature. And what you can see, oops, sorry, that was bad. What you can see here is that the changes in the alpha. So basically, if the environment becomes more uncertain, the learning rate goes down. If the reversal has happened, the learning rate goes down, which is quite strange, but it seems that this is what monkeys do. When they detect more uncertainty, they slow down their learning, perhaps to improve their estimate. Okay, now let me move on to the second experiment. Okay, not second experiment, second set of studies. We try to look at how the animals adjust to uncertainty about the correct model of the environment. And this task is a probabilistic reversal learning task. So there are two options, A and B, and they provide reward probability maybe 80-20, 70-30%, etc. One option is better than the other one. Between trial 30 to 50, there's a reversal, which means that the better option becomes worse option and vice versa. And basically the animal, every session, every block of trials, they're presented with two new stimuli. Then they have to learn which one is better, and in the middle they switch, and then they do the task. Now, there are two types of blocks. One is called what blocks and where blocks. In what blocks, the animal has to use the identity of the stimuli to detect the right answer. So let's say in this case, in B, A is the better option. So the animal has to choose A more consistently. In the where block, the identity of the stimulus doesn't tell the animal what to do, but it's this location. So going left, for example, is the right thing to do, versus going left is the right thing to do. It's a correct behavior, but the identity, whether it's A or B, doesn't matter. So you can see there is this uncertainty about what is the correct rule of the task. Is the animal should use the stimulus identity or the location of it. And so this task has uncertainty about the correct model of the environment. So the animal does not know at the beginning of each block what is the rule, how the reward actually is assigned. They have to figure it out, and this uncertainty becomes another piece that didn't exist in the previous model, but it can tell you something interesting. And so, just to add to that, the two versions of this task. In one case, the animals have been doing the what only blocks all the time. So only the identity matter, and for 2 years that's what they have been doing. In another case, they have a mixture of the two. So this is the uncertainty that I was saying earlier, that basically the animal have to figure out what is the rule on every block of trial. So it's a more challenging task. And so these are the data, published data from Bruno Averbeck's lab. And while they were doing this experiment, they also look at lesions of amygdala and ventral striatum to see the importance of these areas to these types of learning. So just looking at very simple performance, this is a probability of choosing better option in one of the schedule. So as you can see, trial 1, the animal doesn't know anything. They figure out, they choose the better side, let's say around 80%. The reversal happen, the performance goes down and come back up. So the black is the control animals that have no lesion. And then the red and blue are the striatum and amygdala lesions animals. So what you can see here is that if you just look at this task, where you look at what task or where task, the rule is based on the location or action versus the stimulus identity. You can see that when you have a striatum lesion, the performance drops. Amygdala does also affect the performance, but it's much larger in the what task than where task. So people interpret this as striatum being very important for stimulus-based learning. And it's not clear what amygdala is doing. Amygdala has been given many different roles. But now what is puzzling here is that if you look at the what only task, where the animal have been doing what task for 2 years, now you can see that the performance of ventral striatum lesion animals actually better than amygdala lesion. This is basically, there's a reverse between the left and middle panels. The red and blue are switched. And that is puzzling, because if you believe that ventral striatum is important for learning about stimulus, why then the amygdala lesion animals are doing so much work? So how we can get to that? It seems that there is an impairment for both stimulus-based and action-based learning when you have lesion to amygdala. Now, what we can do, we can calculate these metrics that I mentioned to you, these ERTs, on two different ways. One, based on the action. So you're asking how consistent the animal's behavior is in terms of staying on the same action, let's say going left or right, depending on the reward feedback, or based on a stimulus identity. So you're basically asking where is more information or less surprise? And you can see that in the what only task, the action entropy is very high, which means that the animal basically know that they shouldn't care about action because they have been doing this task based on the stimulus for a long time. The ERTS is 0.5, which means their behavior is consistent. When they get reward feedback on A, they have a tendency to go for A. If they don't get, they have a tendency to go for B. When you look at the what task, when the animal doesn't know what is the rule, but the block is a what block, you can see that they go higher. So they become more inconsistent. And the reason is that there is uncertainty. And then the ERTS for action becomes lower. So it looks like they are considering action as well, even though that's not correct. And if you look at the where task, where blocks, where the action is the correct rule, you can see that now the ERTS for action is lower, just like in the what task. So you can see these are the what and where tasks are symmetric. The animal is able to switch the correct rule and perform the task. It's a very different story in the what only task. Now it gets more confusing if you now consider what happened with amygdala and striatal lesions to striatum. So the one thing that I'm not going to details of it, you can see that the same trend exists, basically the correct model of the environment. So here is the stimulus, they are lower. So this basically the solid lines in panel D, lower left, are lower than the dashed line. So the animal is consistent in responding to reward and a stimulus. Now you go to the what task in the middle, the thing is reversed, and the same with the where task. Now we expect that the animal followed the actions. So what you can see, what you saw in terms of the behavior also is reflected in ERTS. What it tells you is that the animals actually have problem, especially if you look at the amygdala lesion in the middle row. You can see that action-based ERTS are lower than up stimulus space, which means that the animal is following action more than a stimulus, and they should not do that. But they slowly learn and switch to the other side if you give them time. But this basically gives us some hint that what is actually what is happening is that these animals are not able to arbitrate between the two systems. So, and we have more evidence for that. Um, if you look at these metrics over the time course of the experiment, I mean, 2 years of experiment, you can see in the what only task, when for a striatum lesion group, so they have intact amygdala, you can see that their stimulus-based ERTs go down. They become more consistent in responding to reward based on a stimulus identity, and less consistent with action. So basically, the way we can explain this data is that these animals getting better at incorporating reward, associating reward with a stimulus. They're able to suppress the action-based system to go with the stimulus identity. And this does not happen so much for the what and where task, except again for striatal lesion animals. What you see is that for amygdala lesion animals, there is no change over time. Basically, the way they look at, they can use the two learning system based on stimulus and action are not really interacting with each other, and is not changing over time. So, and you can see that now, again, you explore these things, you can see that if you feed the data based on a model that has competition between action-based and stimulus-based learning, you can see that the model that has a competition is the best model, which tells you there is interaction between the two, and you can look at the parameters of this model and figure out that the animals, what is happening is that when you have amygdala lesion, the interaction becomes weaker, which is basically not enabling the animal to arbitrate between the two models, to suppress the wrong model of the environment, and so on. So, in summary, what I want to show you from this first part, and I'm a little over my time, is that both species we're looking at here, mice and monkey, adjust their behavior to uncertainty in the environment, but with different mechanisms. When there's uncertainty about the model of the environment, multiple systems seems to be contributing to choice behavior, both action-based and stimulus-based. And amygdala seems to be important for arbitrating between the two systems. So this is a new role that we have been able to identify using these metrics and diving into. And what I didn't show is that this arbitration seems to rely on is controlled by the reliability of the two learning systems, which comes from predicting reward outcome. So it's going back to what I started, is that there are regularity in the environment. In this case, action or stimulus predict reward outcome. But there's uncertainty about how good this happened, and which is the notion of how reliable they are. And so this controls basically what the animal is doing. So this constant adjustment we have in behavior is controlled by prediction and deviation from prediction and uncertainty. Now, The last thing I want to say, hopefully in like few minutes, I know I need to stop soon, is that how this environmental uncertainty get to the behavioral adjustment. There need to be some neural adjustment in the middle, and the question is how we can measure that. As I mentioned, to detect this uncertainty, you need to integrate information over time. So with that, we have developed recently a method to measure the time scales of basically integration of different signal at the level of neural activity. This is 2 years ago. You can read this paper, and so this can be used to basically feed neural data, fine rate activity, and from there we can see that the different time scales and across different cortical areas, we can see this. There is a hierarchy of these time scales, so the time scale of integration gets larger as you go from association area like lateral from LIP to higher cortical areas like ACC. So um, I won't discuss that, but in the interest of time. But there is a relationship between the time scales at the neural level and the behavioral one. So basically, across all these areas, we can see there's a correlation. So when we see that the neural time scales at the single cell level is larger, the animal also integrating that information longer. It's not a causal relationship, but it shows that these time scales are relevant. So the time scales that we see are reflecting the firing rate of neurons are related to the behavior. Now, one question that we can address, and I'm trying to be very quick here, is that whether these time scales of integration reflect something about the environmental changes. So we look at this data set from a task from Dale Lee's lab, where the animal has to choose between two options, and there's a reward probability signaled by the color and the reward magnitude shown on the screen with these dots, as you can see in the timeline over there. And the animal has to choose between them, but the reward probability can switch every 20 to 40 trials, or it can be stable. So basically, you have an environment which is volatile versus an environment that's stable. And the question is that whether this volatility in the environment can change the integration at the level of single neurons. So what we did, we used the same methods that I mentioned to estimate these time scales, and you can see there is a hierarchy, and it seems that the animals are integrating what happened, action, and a stimulus identity in this case. And what is more important is that between stable and volatile environment, some of these time scales are different. So specifically, we found that the reward memory time scale, so how well these neurons are reflecting previous reward feedback, gets larger in a volatile environment. The time scales get larger, and for a stimulus, basically gets shorter. And what we find for reward is actually not expected, because people assume that in more volatile environment, the learning rate should go up, which means that the reward memory should go down, and this is the opposite of that. And I can tell you more about that, why we think this is actually more reasonable. But the idea is that you can actually detect this, and if you look at the changing the time scale of neural integration, like reward memory integration in this case, and the change in decoding accuracy of the firing rate of neuron trying to detect, let's say in this case, reward, they are correlated with each other. So time scales change allows better readout of the neural response, which is very useful in uncertain environment if you try to actually detect what is going on out there. In summary, sorry, I had to rush through this, but in summary, what I want to you remember is that there is a hierarchy in cortical areas in terms of what they are integrating, especially with reward and choice, things that are important for the behavior. And it seems that higher cortical areas have longer time scales. And this longer time scales is important because if you can integrate on a longer time scale, you're basically reducing certain types of uncertainty in the environment, which is not always good, but it's good if you want to control something at the lower level. And we found some detail about, which may not be important right now, in the interest of time, that there are differences in terms of cortical hierarchy, in terms of what they are integrating and whether they are changing, they're responding to the volatility in the environment. Um, but nonetheless, these changes are relevant for behavior and for readout of neural activity. So basically, they allow the neural activity to be more readable by other cortical areas, etc. So I would stop here, to the work, to acknowledge people who did most of this work. Idan Trepka, who was an undergrad in the lab, Meron Speedman, who was a former PhD student, and Jae Hyung Woo, who is a current PhD student, and all our collaborators. And thank you for listening. Let me see. Okay.
Thank you very much for an interesting talk. If there is any question, we also have panel that people attend in another room with you for half an hour, I think.
Mhm.
Okay. So if there is any question, you can ask anybody. So I have one question.
Yes.
What about using the transfer entropy in your information analysis? If you use it, how the result would have changed? Because it's a conditional mutual information that you can assign history as well.
Yes, that's a very good question, and people have been using that, for neural data as well. And so some of the so this is what we try to do here. We play with the transfer entropy as well, but we haven't published anything with that. But what we tried to do here was basically trying to look at the simplest association change in behavior as a result of what happened. And because the way people think about reinforcement learning is that there is a um, there is a trial by trial change in the behavior that is informed by what happened, and so it's kind of accumulate over time. So in some cases, it could be confusing if you add the history on top of, well, what is causing basically the change in behavior, if it makes sense. But it is an important concept that one could introduce and could be very important for detecting certain things. Um, but we are also trying to see, using just conditional entropy, also the recent history of reward, how it impacts basically behavior and adjustment behavior.
Any other question? Okay, there is one.
I can't hear.
Okay. Um, Hello, can you hear me?
Yes, I hear you. Yes.
I guess you can. Thanks for your perfect lecture. I just have one question. If you have any hypothesis about the ecological uh, behavior in other species except mice and monkeys in their increase in their entropy, so I'm just wondering, is it related to their ecological behavior or not? I mean, their social behavior that they have in their population. Is this entropy related to their social behavior or not? That's it.
Very good question. So oops. Um, yeah, the questions of whether we can use these entropies to detect something about maybe randomness in the behavior because of the maybe social hierarchy, maybe interaction with other members of species. So we have been very recently trying to apply this um, to some um, game theory data, that where you can actually introduce kind of social interaction between different agents. Um, and what we found so far is that you can see the effect of, uh, let's say, social hierarchy. This is playing some sort of matching pennies game between different baboons, that they have different hierarchies, like they can be higher or lower rank, and you can see the impact of that on the how noisy or inconsistent the behavior is. So it's definitely important why the animal would change their strategy in terms of being less or more consistent depending on the task demand and depending on the social structure of the environment. And these are there are many questions to look at, and yes, we have started to look at it to see if we can reveal something in addition to what people know, because as I showed you earlier, you can calculate this overall entropy, which measure how noisy or inconsistent the behavior is, but also you can measure the entropy in terms of the link to reward, mutual to the reward feedback in the previous trial, mutual information, etc. You can also, um, as mentioned, transfer entropy. You can do all sort of things to look at to see what is changing actually, because some of these things, let's say increase in randomness in behavior, could be caused just by having more noise in the system. I don't know how maybe in some neurotransmitter can increase the noise in decision making that people measure with uh, um, beta temperature in the reinforcement learning model. But it's very easy to blame many things on that. But the point is that we can zoom in and figure out whether this is really related to choice, stochasticity in choice only, or there's a learning component, etc. Um, so these metrics are not perfect because they can also mix few things, but by looking at them all at the same time, you can kind of triangulate and estimate what is happening. And then you can confirm all those things using a model that is trying to test those basically insight from the metrics. So you need a combination of them. But to answer, going back to your questions, yes, we have some evidence that you can use these metrics to study um, um, how this adjustment depend on the social interaction, and it could be more or less important for different species.
That was great, and I'm so obsessed with it. Thank you for your point of view. Thank you.
Thank you.
So any other question? We have one.
Hello. Uh, Hi, Alireza. This is Ali Ghazizadeh. I just wanted to thank
Hi.
you so much for joining us this early in the morning. It's I think it's 5 a.m. or something.
Now it's 6:30. Thank you for
We
inviting me.
what is that?
It's 6:30, but thanks for inviting me. I'm
Oh, I
awake
see.
now.
Yes.
Thank you.
Yeah, so we really appreciate you and the fact that you could wake up this early in the morning and give this interesting talk. A lot of the people here are familiar with the concept of entropy and Shannon theory, and especially people from electrical engineering background, communication theory. And I think it's very interesting to see how these simple fundamental ideas can be used to have better understanding of the behavior, complex switching behavior as you described. I just wanted to take this opportunity and thank you again for being with us. There will be a panel afterwards for people to get in a bit more in-depth discussion with you, and I hope you can hang in there for another 20 minutes or so.
Sure.
since very many students would be interested to hear your insights, both from your work and also professional development aspects. We have some people with physics background like yourself. They may be interested to come into neuroscience, and I think your kind of research and educational history would be very useful for them. Thank you
Thank
again.
you. No, thank you for having me here. It's really a great pleasure for me to. I wish I could be there. I haven't been there for, I don't know, 20 something years after I graduated. And yeah, so it's a great pleasure for me to talk with students and faculty there. But also, as you mentioned, I want to just emphasize what we did here is a very small thing, like using something that people actually use all the time, but nobody bothered to actually apply it um, to neuroscience, basically, or to understanding behavior. And so people there who have very good mathematical and engineering background, they're familiar with these concepts. Yes, there's a lot of interesting things to do, so they should feel brave and motivated, trying to use some of those techniques to understand behavior and neural data. So there's a lot of room actually to investigate these things, as you can see here. So we are talking about the concept developed 70 years ago, and now somebody's using it trying to understand behavior. So I hope this is motivating students to think about they can do interesting stuff if they find this interesting, of course.
Thank you very much for your time and the interesting talk. I think there is no question and we can end this session. Thank you very much for your talk. Yeah.
Thank you. So how we move to the other session? Oh,
Sorry, can you repeat?
I said how we move to the other session. I just stay on this thing for the group session.
Yes.
Okay.
Yes, it's the same room. Here's the same room.
Okay.
So when شما بشین آقای دکتر. ای بابای گرم. Okay. Yeah, people getting ready for the panel.
Sounds good.
دوستان پنل دکتر سلطانی همینجا اگه خواستین تشریف داشته باشین.
When people getting ready, can I ask one question? In your
Sure.
graphs, you introduce some alpha and beta, but you didn't introduce the equations for that. It's kind of the temperature as in physics, or
Yeah. So alpha is the learning rate, and beta is the inverse temperature that you have in the reinforcement learning model. So beta basically measure the randomness in choice behavior. Sorry for not mentioning that. Yes. Yeah, it's like the temperature you have in Boltzmann machine, but they use similar concept for the
okay. And now
for
here, what is the exact meaning for that? For Boltzmann, I know what the temperature means, but
so
here,
in the reinforcement learning model, basically you have two estimates of value for option A and B, and then you map them on the sigmoid to detect the choice probability. So if and then so it's basically a sigmoid function of value of A minus value of B divided by that beta. So So that's basic. If beta is large, your sigmoid function is shallower or steeper, which means that you are sensitive, less or more sensitive to the difference in value. So you have estimated the probability for the two options, and then you want to make choice based on that. So if beta is large, it means that you're not very sensitive to your estimation. And if it's small, it means you are very sensitive to that. And nobody really knows where this temperature, what we call the stochasticity in choice, come from. It's at something at the level of, could be related to networks, how it's wired, but really nobody knows, and people just estimate it to measure how stochastic the behavior is. Also, similarly, they use it to talk about exploration versus exploitation, like how much you're exploring compared to what you know. Does it make sense?
Yeah, there's a trade-off between these two. Okay,
Yeah.
so any question? Okay.
Alireza, I'm Irfan, and I'm with biology of life science, so I'm not familiar with physics. But as far as I know, I've reading one article that discuss about the en- when the entropy of our system increases, the chance of creativity also increases. But in your finding, I see something different, that monkeys act different than mice. So I cannot understand this, because again, in evolution we said when our entropy increases, again
Uh-huh.
creativity of environment and the species increases. So I'm just little confused.
Yes, it's a good question. And as I mentioned, people using mostly normative approaches, they try to make an argument that something, let's say like volatility in the environment, should result in one thing. For example, the assumption is that if you are in a volatile environment, the environment is changing very quickly, so everything you know basically get outdated very quickly. Like this is better, but then tomorrow is not better. Just like the situation in Iran. So you have volatility, and the idea is that many people think that that should increase the learning rate. What it means is that you have to learn faster, you have to update faster. So that makes sense. And people, the way it makes sense is that people have measured, um, for example, you can calculate in a task whether increased learning rate would give you more reward overall or not. So that's the logic, is that you can improve your performance if you have more learning rate. I would argue that this is not completely true. You need to really create a situation that is true. The changes are very small. In terms of being ecologically valid, I don't think the animal can perceive the difference between 70% and 65% reward. There is no way on multiple choices. So what is to me more important is that you can, and that's what I said, like we see in different species, they do different things. It could be task dependent. So it's not like, oh, this is what mice or monkeys do. It's they do it in this task because the way they were trained, because of basically what, I don't know, the actions or stimulus means for them, etc. But the idea is that you could potentially increase your learning rate, become less consistent in your behavior to adjust faster. But sometimes it's also useful to shut down learning so that you can um, use some other information to make choices instead of trying to fluctuate up and down very quickly. So it's not entirely true that volatility increase learning rate. Actually, there is only one paper that provides evidence for that, and there is no replication of that. But people assume that's the case because, well, it makes sense. But it doesn't really make sense. It only makes sense from the point of view of increasing performance, but it does not in terms of other things. So what my usually the way I try to understand these things is that um, if you think about goal-directed behavior, the goal of the animal is to survive. That's really what it matters. So, and then when you think about the survival, meaning your survival is to achieve a goal. The goal could be getting the next reward, etc. The way you can achieve it can change massively from one time to another time, which basically tells you many aspects of behavior need to be flexible. to survive. And so it really doesn't matter if the reward rate goes up or down. The important thing is that you can achieve a goal, which is next meal, let's say, for an animal. And so if you look at animals' behavior, for example, let's look at the risk attitudes, right? Risk aversion, the fact that we like sure option more than risky options. If you look at animals' behavior in nature, what you can see is that in the morning and in the evening, the type of prey, for example, a cheetah would go after, is different. It's not the same thing. So they go for larger prey at the beginning of the day and the smaller and at the end of the day. And the reason is that their physiological state is different. They're a different level of hunger. So at the end, you're happy to get something smaller. So I don't think there is anything that can explain like, okay, this is how it should be. And I think should be understood from the point of view of goal-directed behavior. And you mentioned creativity. I will look at it in terms of intelligence, is that your goal as an intelligent agent is what is the goal. I don't think the goal is ever to get the maximum amount of reward. That is not. I personally don't think that it is. But the goal is to survive. And that survival means that different things at different time point. And so it makes it very difficult and messy to understand what is happening. But that's how it is. The brain is messy and the behavior is messy. But so I hope
Thank you so much. And my last question is about further reading, because that was my first exposure to this kind of uncertainty research, and really want to pursue more about it, and it's triggered my curiosity. So do you have
so
any
you can so that we
suggestion
have
for me to find new references, or can I get more in touch with you?
yes, please, you can do that. So we have two papers on this topic. We're doing a lot of studies on this. They haven't been published, but the two papers, one in 2021, and there's another one that just came out. These two, if you read them, you get a good sense of what I mean by these things. And then, yeah, there's also, if you're interested in time scales and how they relate to uncertainty, there's a review paper that I've written with a bunch of other people. But in terms of the entropy metrics, you can read the 2021 and 2023 papers that we have written on this topic, and it should clarify a lot of things. And we try to also some speculate about different species and why they are different.
Because of your how can you manage all of these fields together, and that was amazing. Thank you, and have a nice day.
I guess we have some questions in mutual class, if it is possible to give them the accessibility.
There is a question from an online person,
Hello?
Amir Hossein Najibi.
Okay.
The microphone is on. You can talk.
Hi, can you hear me?
Yes.
Yeah, thanks for the fascinating lecture. Actually, I've got two questions. First, I may not have grasped it completely right, but one conclusion was that the reward memory time scale increases with increasing volatility. And I was wondering how this makes sense, whether this is logical, because I'm not sure if this means that by increasing reward memory time scale, you mean that the agent depends more on the previous reward for making decision, or less. I'm not sure, but if it means depending more on the previous reward, how does it make sense in a volatile environment? Because we expect the agent to be less dependent on the previous reward, because we don't know, it is constantly changing.
Yes, good point. That's what I say is paradoxical. So you're right that in this task, not the general argument that if you have a less and more volatile environment, the more volatile environment actually means faster learning. This, I would argue that this is not true. It's theoretically correct, but it hasn't been shown really behaviorally. In this task, in the data set I showed, it's true, because the stable and volatile environment are fully indefinitely stable and volatile. So in one case, nothing changes in terms of reward probability. In the other case, it changes. And if you look at the behavior, yes, the behavior tells you that the learning rate is faster because they're actually not learning anymore in the stable environment. So in the volatile environment, compared to fully stable environment, the learning rate is higher in the same data set. So I'm aware of that, and that's why I say it's paradoxical. Now, what it means that, as you correctly realize, the longer integration of reward memory means that the neurons in those areas that we look at remember reward outcome on a longer time scale. Now, the question is whether that is going to influence the behavior or not, because the behavior is going in opposite direction. Now, how can you put them together? Is that so? One aspects of let's say dealing with uncertainty could be looking at reward feedback to control the behavior. And so, in that sense, you're right that yes, if I don't care about the previous reward, which means shorter time scale, maybe I can be more useful, right? But you are just ignoring reward feedback. I argue that in a volatile environment, you may want to actually have a longer memory of reward so that you can detect it. Even though it's not influencing your behavior directly, you can use that longer memory to detect actual changes. Does it make sense what I'm saying? So put it this way, if you have a 2 running average of performance or any signal you can imagine in the world, you need to have them on different time scales. You need to have something on much larger time scales so that you can compare it with the shorter one so that you can detect if something's happened. And so they could serve something like that. And in more volatile environment, you may need to actually have even longer memory to be able to make that comparisons, not to control the behavior, but to adjust the behavior later on. Do you see the difference? The difference is that whether I'm listening to the reward feedback just happened versus whether I am adjusting my overall strategy because I know that the reward has been like this in this environment. And so not here, but in another work we publish in Nature Human Behavior, we compared actually monkeys and human in terms of how they use volatility in the environment to change their behavior. And what we found there is that there is no change in the learning rate, but there is change in other things in terms of how they combine information. So what I want to say is that we need to think outside this simple explanation of learning rate, which is very misleading, and think about there are many pieces of information in an environment that the animal needs to combine to make choices. It's not just about updating. There are other information, there are other things that are important. And so having a longer memory of reward in a volatile environment can be very useful for those processes, not for learning, but for those other processes. And those other processes we have shown, not here, but in a different paper that actually use some of this data set here, is that there are other changes in the behavior that are far more important than changing the learning rate. But because people who have been thinking about this question, I believe, have been very strongly influenced by computer science and the notion of agent in an environment and update, and you always have one variable, of course, when you're looking at those kind of questions, is this notion that the learning rate must have changed. We need to learn faster. That's all that matters. No, there are many other important things, and behaviorally, those are more important, as I mentioned earlier, than changing the learning rate. If you have slower learning rate or a faster learning rate in a volatile environment, if you look at the performance in terms of reward rate, the difference is very tiny, very tiny. But there are other things that are more important.
Yeah, that's very fascinating actually, because like you mentioned, that's the whole paradigm of reinforcement learning, and this shows that a true animal making decision is more than just a reinforcement learning agent making decisions. But thank you very much. And my last question is that do you think there is a chance for studying fight or flight behaviors through this entropy based approach? I mean, because essentially there is the concept of reward is less prominent in such situations. So the animal
Yes.
either gets a punishment or doesn't get a punishment. So it's basically fighting for survival.
Yeah, you can do anything. I mean, I'm just claiming very general. The reason is that these are just based on conditional probabilities. It's all about probabilities, right? So you can put anything you want. You can pair anything with anything. So a punishment, it doesn't have to be a reward. It can be previous choices, can be anything. The point is that you can put any variables and see how they happen together or not, and then you go from there to information theory.
Do you
And
know
then you
any
can
available
extend.
papers?
Sorry.
Any available papers on that? I mean, like any further
No,
reading?
nobody has done anything. That's what I'm saying. There's a lot of interesting thing to do because
Mhm.
it's an open field in terms of exploring. Because the way people have been thinking has been very limited in certain way, and I don't know why people just haven't looked at that. But yes, we are started looking at it, and if you read those papers that I mentioned that we have published, basically you can see the logic and what you can do with them and so on. But exploring them in other fields, yeah, if you want to do that, let me know. But nobody
Yeah,
has
thank you.
done that.
Thank you very much.
Sure.
Hello.
Yes.
Good. Thanks, Alireza, for your brilliant presentation. I'm
Sure.
a PhD student of cognitive neuroscience. I have a more general question for you. As you know, uncertainty and tolerating uncertainty has a large literature in management, economy, psychology, etc.
Mhm.
Do you believe that your research have can shed light on those type of research? I mean, for example, uh, there's a large research on entrepreneurs or innovators that
Mhm.
how they tolerate uncertainty more than other people.
Yeah.
So uh,
Yeah. I think it's a.
I just want to have your point, your message. Uh, does your methodology, your kind of research, help in any kind?
Yes, so it's a very good point. Thanks for asking it, and it's a topic of entirely different talk, but not the specific method that I mentioned here, but a general framework that I pursue in my research, which is trying to understand what uncertainty does to flexibility. There's a link between the two, and it's a very clear link, and but people usually try to understand this link and this framework in terms of very rigid concept in cognitive neuroscience. So either they go from the point of view of rationality and rational decision making, trying to apply normative approaches, or try to actually look at biases and heuristics that people have, try to say, oh, how we are not good, etc. But I think we have to, if you focus on flexibility as the most important thing for survival. So just think about survival and think about how flexibility is important. If you think in terms of those concepts, then the meaning of intelligence in terms of achieving goals in different environments become very tightly linked to the notion of flexibility. So this big framework of trying to understand the flexibility in behavior, it has important implications for how we can be maybe more successful species in terms of adjusting to our environment. Because it's very surprising that on one hand we are equipped with all sort of machineries in our brain to deal with uncertainty. At the same time, as human species now, we are obsessed with controlling uncertainty in our environment. Like we try to control it. We hate the uncertainty. We just can't take it. Want to freeze everything to not have uncertainty. And if we let go of that and try to understand and appreciate what we have evolved for, which is surviving under uncertainty, you can see much better, basically, much better like what we can do and how we can use those things instead of feeling like, oh, how we can deal with anxiety related to uncertainty, etc. I mean, of course, this is a scientific thing and maybe doesn't apply or useful for people, but who, let's say, suffering from too much uncertainty in the environment. But the point is that there is something to be appreciated there in terms of how the uncertainty can help us to be more flexible, and that is very useful.
Many thanks. Thank you, Alireza.
Sure.
Thank you very much for the panel. We ran out of time here, and we stop the questions right now. Thanks for your talk and the time for the panel.
Thank you very much for